Hello everyone, welcome to ashatech.com. Today we are discussing the DC electrical circuits and we have a guiding question as follows. State Thevenin's theorem. Part B, outline 4 limitations of Thevenin's theorem. Part C, for the circuit given below, draw Thevenin's equivalent circuit with a 16 ohm as the load resistor and calculate the current through the 16 ohm resistor. So this is our circuit, and this is the 20 voltage source, this is the 30 voltage source, this is a 16 ohm resistor which is acting as the load resistor. R1 is 4 ohm and R2 is 24 ohms. Let us look at the solution for this particular problem. This is Thevenin's theorem. Thevenin's theorem states that any linear electrical network having voltage sources, current sources, and resistances only can be replaced by an equivalent voltage source called Thevenin's voltage in series with an equivalent resistance called Thevenin's resistance. That is particularly Thevenin's theorem, that any complex network of resistors and sources, that is independent sources and current sources, can be replaced by an equivalent voltage source called Thevenin's voltage, and which is in series with an equivalent resistance called Thevenin's resistance. Part B says the limitations for Thevenin's voltage, and now this is answer number 1, that it cannot be applied to networks with nonlinear elements such as transistors and diodes. Analyzing a circuit with transistors and diodes is not really easy to analyze it with Thevenin's theorem. Number 2, in circuits where there is magnetic coupling between the load and any other circuit element, Thevenin's theorem cannot be of any help. For example, where you have inductive rods, where you have any kind of magnetic coupling, really Thevenin's theorem cannot help you to analyze such a circuit. Number 4, Thevenin's theorem cannot be used in circuits containing load in series or parallel with controlled or dependent sources. Where you have dependent sources or controlled sources, then you cannot use Thevenin's theorem. Lastly, that it cannot be used in circuits with unilateral elements such as diodes. Actually, the circuit must be bilateral. So where you have unilateral components, for example diodes, you can never use Thevenin's theorem to analyze that particular circuit. So let us just look at these are just notes. The procedure adopted when using Thevenin's theorem is summarized as below. To determine the current in any branch of an active network, for example one containing a source of EMF, you have to remove the load resistance RL from that network. For example, if you asked anything concerning that particular resistor, you remove it from the network. Determine the open circuit voltage EC across the break. Remove each source of EMF and replace them by their internal resistances, and then determine the resistance RTH, which is Thevenin's resistance, looking in at the break. Then determine the value of current IL from the equivalent circuit as shown below. You can use this particular formula. IL is equal to VTH over RL plus RTH, and this is just application of Kirchhoff's law inside a loop. This is Let us move ahead and look at our question, part C, which requires us to use Thevenin's theorem to find the current flowing through the 16 ohm resistor. Now, this is the 20 voltage source. The sources are intact. This is the 4 ohm, the 24 ohm. So if we remove that resistor and the 16 ohm resistor, we remove it and substitute it with the voltage source at that moment we called Thevenin's voltage, then we can now use even KVL. I use the KVL in this particular loop to calculate for I. So current flows, if we assume that the direction of current is this way, then it means a current is flowing from the 30 voltage source through the 24. Here is open, so current doesn't flow through it, and it will proceed to 4 and throughout the closed path around that rope. So this means if we apply KVL, it will be 30 minus 24I, because it is leaving positive and here entering positive but leaving negative. So 30 minus 24I minus 4 times that current I minus 20 and is equal to 0. So 10 will therefore equal to, when I look at this and that, I collect like terms together. Therefore 10 is equal to 28I. Therefore I is equal to 10 out of 28, which is equivalent to 0.357 amps. So having gotten a current flowing at that open circuit, I mean flowing when that resistor is removed, let us now substitute it with VTH. So this VTH is Thevenin's voltage, and we are going to consider loops such that we have loop 1 and loop 2. So using KVL, we apply it to loop 1. This will mean our current is flowing at 0.357. So it will be 30. Again, this is a plus, this is minus. This is a plus, this is minus. So 30 minus I times 24, so that will be minus 24 times 0.357, then minus the voltage here. The voltage here is VTH. So minus, because this current is flowing like this, so it enters this source here as positive and leaves negative. So minus VTH is equal to 0. So when we simplify, we find that our Thevenin's voltage is equal to 21.43 volts. What about when we apply? Let us check our answer by applying KVL in loop 2. So when we apply loop 2, it means current is going to be flowing. We are assuming that current is flowing from this VTH source, the Thevenin's source. Then it means V Thevenin minus 4, it is entering positive, leaving minus, so it will be minus 4 times the current, 0.357, minus current entering here positive, leaving negative, so minus 20, giving you 0. So VTH is equal to 20 plus 0.357 times 4, it gives you 1.428. This gives you 21.428, which gives you 21.43. So our answers are right. Now, Thevenin voltage is obtained. Our task now is to find the R Thevenin. So calculate RTH, R Thevenin, which is the effective of the parallel connection. When you look through in between here, you see as if current flows this way and also that particular branch. Therefore, the 4 and 24 ohm resistors are parallel. So when we use product over sum, it means you have a product over sum because it is a parallel connection of two resistors. So that RTH actually will equal to 4 times 24 divided by 24 plus 4, and this will give you 3.429 ohm. Now let us draw what we call Thevenin's equivalent circuit. Thevenin equivalent circuit, you are going to just draw this voltage source with Thevenin 21.43 volts. Then RTH, which is Thevenin's resistance, 3.429 ohms. Current flowing through is actually also add the load resistance 16 ohms. The current flowing through is load current IL. So from ohms law, even if we use even Kirchhoff, because this is a rule, it means I VTH minus IRTH minus IRL would give you 0. Actually, I can also say VTH minus IL RTH minus IL RL. This would mean VTH is equal to IL into RL plus RTH. So meaning that finally, if I look at it, my VTH should be equal to, actually my IL should be equal to VTH RL RTH. So when we substitute in these values, 21.428 divided by 3.429 plus the load resistance, which is the 16 ohm resistor, then it means current flowing through the 16 ohm resistor would be 1.103. Thank you so much for watching. If you want to check this answer done by superposition, please, you are going to check in the description of this video and find a link which will connect you to the superposition of method which we used to compute this current through the 16 ohms resistor. Therefore, you are able to confirm. Thank you so much.